Where does gold come from? In medieval times, alchemists tried to achieve the seemingly impossible. They wanted to transfer lowly lead into gleaming gold. History portrays these people as easy eccentric, but if only they know their dreams were actually achievable. Indeed, today we can manufacture gold on Earth, thanks to modern invention that those medieval alchemists missed by a few centuries. But to understand how this precious metal became embedded to start with, we have to gaze upward at the start. Gold is extraterrestrial. Instead of rising from the planet's rocky crust, it was actually cooked up in space, and is present on Earth because of cataclysmic stellar explosions, called supernovae. Stars are mostly made of the hydrogen, the simplest and lightest elements. The enormous gravitational pressure of so much material compresses and triggers nuclear fusion in the star's core. This process releases energy from the hydrogen, making the star shine. Over many millions of years, fusion transforms hydrogen into heavier elements, helium, carbon, and oxygen. Burning subsequent elements faster and faster to reach iron and nickel. However, at that point, nuclear fusion no longer releases enough energy, and the pressure from the core peters out. The outer layer collapses into the center, and the bouncing back from sudden injection of energy, the star explodes, forming a supernova. The extreme pressure of the collapsing star is so high that subatomic protons and electrons are forced together in the core, forming neutrons. Neutrons have no repelling electrical charge, so they are released captured by the iron group element. Multiple neutron captures enable the formation of heavier elements that a star under normal circumstances can form, from silver to gold, past lead, and on to uranium. In extreme contrast to the million-year transformation of hydrogen to helium, the creation of the heaviest elements in the supernova takes place in only seconds. But what becomes of gold after the explosion? The expanding supernova shock wave propels its elementary debris through the interstellar medium, triggering a soaring dancing of gas and dust that get dances into new stars and planets. Earth's gold was likely delivered this way before being kneaded into veins by geothermal activity. Billions of years later, we now extract these precious products by mining it, an expensive process that's compounded by gold really. In fact, all of the gold we mined in history could be piled into just 3 Olympic-sized swimming pools, although this represents a lot of mass because gold is about 20 times denser than water. So, can you produce more of this covered commodity? Actually, yes. Using particle accelerators, we can mimic the complex nuclear reactions that create gold in stars. But these machines can only construct gold atoms by atom. So it would take almost the age of the universe to produce 1 gram, at a cost vastly exceeding the current value of gold. So that's not a very good solution. But if we were to reach the hypothetical cost where we mine all of the Earth's buried gold, there are other places we can look. The ocean holds the estimated 20 million tons of deserved gold, but the extremely minuscule concentration making its recovery too costly at present. Perhaps one day we will see gold rushes to tap the mineral worth of the other planet in our solar system, and who knows, maybe some future supernova will recall closer enough to shower us with this treasure, and hopefully not eradicate all of our Earth in the process. One more. In medieval times, alchemists tried to achieve the seemingly impossible. They wanted to transfer lowly lead into gleaming gold. History portrays these people as easy eccentric, but if only they know their dreams were actually achievable. Indeed, today we can manufacture gold on Earth, thanks to modern inventions that those medieval alchemists missed by a few centuries. But to understand how this precious metal became embedded on a place to store it, we have to gaze upward at the start. Gold is extraterrestrial. Instead of arising from the planet's rocky crust, it was actually cooked up in space, and its presence on Earth because of characteristic stellar explosions, called supernovae. Stars are mostly made of hydrogen, the simplest and lightest elements. The enormous gravitational pressure of so much material compresses and triggers nuclear fusion in the star's core. This process releases energy from hydrogen, making the star high. Over many millions of years, fusion transforms hydrogen into heavier elements, helium, carbon, and oxygen, burning subsequent elements faster and faster to reach iron and nickel. However, at that point, nuclear fusion no longer releases enough energy, and the pressure from the core peters out. The outer layer collapses into the center, and bouncing back from this sudden injection of energy, stars explode, forming a supernova. The extreme pressure of a collapsing star is so high that subatomic protons and electrons are forced together in the core, forming neutrons. Neutrons have no repelling electric charge, so they are easily captured by the iron group elements. Multiple neutron captures enable the formation of heavier elements that a star under normal circumstances can form, from silver to gold, past lead, and on to uranium. In extreme contrast to the million-year transformation of hydrogen to helium, the creation of heaviest elements in the supernova takes place in only seconds. But what becomes of gold after the explosion? The expanding supernova shock wave propels its elemental debris through the interstellar medium, triggering a swirling dance of the gas and dust that condenses into new stars and planets. Earth's gold was likely delivered this way before being kneaded into veins by geothermal activity. Billions of years later, we now extract these precious products by mining it, an expensive process that is compounded by gold reality. In fact, all of the gold we mined in history could be piled into just 3 Olympic-sized swimming pools, although they represent a lot of mass because gold is about 20 times denser than water. So, can we produce more of this covered commodity? Actually, yes. Using particle accelerator, we can mimic the complex nuclear reactions that create gold in stars. But these machines can only construct this gold atoms by atom, so it would take almost the age of the universe to produce 1 gram, at a cost vastly exceeding the current value of gold. So that's not a very good solution, but if we were to reach a hypothetical point where we mine all of Earth's buried gold, there are other places we can look. The ocean holds estimated 20 million tons of dissolved gold, but the extremely minuscule concentration making its recovery too costly at present. Perhaps one day we will see gold rushes to tap the mineral well of the other planet of our solar system, and who knows, maybe some future supernova will occur close enough to shower us with treasure, and hopefully not eradicate all of our own Earth in process.